Hello, I am Muhammad Aad and I will be presenting our paper Dynamic Graphs in the GPU published in IBDBS 20. So in real life, graphs change over time and we would like to be able to update the graph through the different operations such as edge insertion and deletion, vertex insertion and deletion, and we would like to be able to perform these operations at high throughput. And in our approach, we use a hash table based graph data structure. The key motivation for using a hash table is that the traditional techniques of using a list to represent the adjacency list requires the additional cost of sorting the adjacency list in the beginning and then maintaining the sorting order after updates. And using hash tables, we can avoid this overhead. Now I will give a brief overview of the current GPU graph data structures. And typically we have a vertex dictionary, and for each vertex we have a pointer to its own adjacency list. And in CSR or compressed sparse row format, all of the edges are compacted and stored inside a fixed size array. Now this is the most compact form, but if we need to update the graph, we have to rebuild the whole data structure from scratch, which is not practical when it comes to a dynamic graph problem. A different approach by Hornet, a different graph processing framework, is to store the adjacency list of a vertex inside a variable size array. And if we exceed the capacity of an array, we double its size, then we copy the edges to the new array. So we still have to do some copying, but we don't have to copy the whole data structure. Another approach taken by FameGraph is to use a GPU linked list to store the adjacency list of a vertex. And if we exceed the capacity of one of these linked list nodes, we allocate a new node and we link it to the previous one, and this node size can be configured by the user. Now the problem with all of these approaches is that if we need to perform a query operation to maintain unique edges, for example, if the array is not sorted, the cost will be linear. Now we can sort the adjacency list to improve the query performance, but then we add the additional costs of maintaining the sorted order, which we can avoid if we use a different data structure such as a hash table. So our data structure is hash table based, and for each vertex we store a pointer to its own hash table, and we use SlabHash, a GPU dynamic hash table that was designed in our group as well. And we also store additional metrics such as the number of edges per vertex, and if we construct the hash table with the right load factor, our query performance will be done in constant time. Now I will give a brief overview of SlabHash. So SlabHash is a dynamic GPU hash table, and given a load factor, it defines a number of buckets. Each bucket is a 128 byte slab, and if collision happens, we can allocate a new slab and link it to the previous one. So initially SlabHash supported concurrent multi-map, which allows non-unique keys, and we added support for concurrent map to ensure keys are unique, and we use concurrent map in unweighted graphs. And we also added concurrent set, which stores keys but no values, and this concurrent set is used for unweighted graphs. Now our graph data structure supports different operations, and we break them down into three categories. The low-level operations such as edge insertion and deletion, vertex insertion and deletion, bulk build, so given a graph in a COO format, build the graph, and queries such as an edge exists query or an iterator to read the adjacency list of a vertex. Now I would like to highlight one of the design decisions that was used in SlabHash and we use as well in our work, which is a warp cooperative work sharing strategy. And in this strategy, each thread has its own assignment, but the processing is done with warp. So we can break this strategy into three steps. The first one, where we build a queue of the new operations we would like to perform. Then we perform each of these operations one at a time using the whole warp. And finally, we maintain any additional metrics that we would like to maintain, such as the number of edges per vertex. And the benefits from using this strategy is that it eliminates branch divergence and it allows for collapsed memory access, which means better memory performance. Now, one of the contributions of our work is that we try to define a set of benchmarks to evaluate a dynamic graph data structure. And we break these benchmarks into three categories: low-level operations, workloads, and applications. So in low-level operations, we evaluate the performance of the different operations such as edge insertion and deletion, vertex insertion and deletion. And in workloads, we try to simulate what real-life scenarios will be. So for example, if we already know the graph, we can bulk build it, or if we are starting from scratch, we can incrementally build the graph. And we have as well the application, or solving a graph problem, which can be a static problem or a dynamic problem. And in our work, we use a triangle counting example to show as an application. And in our evaluation, we compare our performance to Hornet and FameGraph, two different graph processing libraries. Now, to evaluate our data structure, I will start by comparing the runtime of sorting CSR to building our data structure. And the idea behind this comparison is that we can think of any of the other data structures, the alternative data structures, as simply sorting a CSR, then maintaining that sorted order. So let's just compare the sorting runtime to building our data structure. And we see here that just building our data structure is orders of magnitude faster than sorting CSR, which proves our point that there is an overhead that we can avoid if we use hash tables. Here we compare the performance of the low-level operations, and we see that using hash tables allows us to outperform the list-based techniques, and we see speedups in all of the low-level operations. And for the workloads of building the graph, we see speedups in both of the scenarios: incremental build, where our performance is 5 times faster than Hornet, and bulk build, where our throughput is up to 30 times faster than Hornet. And an interesting note here is that Hornet spends almost half of its time for this dataset just making sure that the graph contains unique edges, and which is the same time that we actually need to build our whole data structure. And here we evaluate solving a dynamic graph problem using our data structure. And we pick triangle counting as an example. And the core operation of triangle counting is the intersection operation. So intersection means, given two adjacency lists, count the number of common vertices between these two lists. And we can break down the dynamic problem into two phases. The first one, where we compute the intersection, then we follow up with updating the graph. And we see that there is a trade-off between these two phases. So we find that performing the intersection operation using sorted lists is faster than using hash tables, but the high throughput during updates makes up for this slowdown. So just for after 5 rounds of updates, we can achieve either similar performance to Hornet or almost twice as fast as the Hornet. So in conclusion, we showed that our hash table based dynamic graph data structure offers superior performance compared to the alternative list based graph data structures. Using hash tables allows us to avoid the overhead of sorting the adjacency list and the overhead of maintaining that adjacency list in sorted order. And there are a few design decisions that we can revisit. So first, note that vertices have different workloads in terms of updates and queries. So how often are we going to update a vertex adjacency list, and how often are we going to, for example, query or read the whole adjacency list of a vertex. And this trade-off is controlled by a load factor. And although we use a single load factor for all of the vertices in our work, we can set a specific load factor for any vertex. But then we have to figure out the right load factor for each vertex on its own. So hash tables might not well suit all of the graph problems. For example, we found that a sorted adjacency list is useful when performing the intersection operation. So we can replace the hash table with a data structure that by construction maintains a sorted order, such as a B tree. But still, there will be always a trade-off between how fast we can solve the graph problem and how fast we maintain the data structure. We also support concurrent updates and queries, but then an application needs to carefully consider the semantic of these concurrent operations. Finally, we are still lacking real-life dynamic graph workloads, and we would like to investigate more into these workloads. So thanks for everyone who supported this work. Thanks to Martin, our collaborator, and people from our group for their help. And finally, if you have any questions, please send us an email. We will be happy to answer your questions. And our code is available in GitHub, so please feel free to open issues if you have any questions about the code or about how to use it. And thank you for watching.